Hello everyone, and today we're going to be talking about conditions for optimality. So in the last video we talked a lot about the different optimal functions and how we define a minimization problem and these different kind of programs that we're going to be running. And when I say program, I mean an optimization problem. So let's talk about a little bit about parabolas. So I don't know if you guys did this in high school, but I did a lot. We had a lot of problems where we had to find the minimum of some parabola. So graphically it's pretty straightforward, it's just down here in the center. But if I have a function for a parabola like this, I have some ax squared plus bx plus c. The actual equation to find the minimum is this one right here. So negative b over 2a, and this will give me the argmin. So this is the point at the bottom of the parabola. You can also think of it like the midpoint formula. Let's really break this down and figure out what's happening. So we take our function and we're going to take the derivative of our function. And we take our derivative, we get 2ax plus b. And if we take that and set it equal to 0 and solve for x, what we'll end up getting is the exact same equation we had from the last slide. So essentially what we've looked at is we have a parabola, we want to find the min point. If we use that formula, we get the argmin, and we can derive the same equation from calculus. So what is it really saying? It's saying that our derivative at a specific point is equal to 0. So this makes a lot of sense for an optima, and we're going to look in why that is. So the thing we're going to look at is this thing called the first order necessary condition. And essentially what it says is the derivative at a stationary or critical point must be 0. So a stationary or critical point can be a minimum, a maximum, or something else that we'll talk about a little bit later. So if I have my f prime of x, so my derivative of x is equal to 0, we can really intuitively figure out why this makes sense to be a minimum or a maximum. So let's say I have this function down here, and I take a specific point here, and I calculate the derivative. So I'll get the instantaneous slope that looks like this. So if what I'm trying to do is find the minimum value, my f prime of here is less than 0 because my slope is decreasing. So if all I need to do is take a step in this direction, and I get a new point that has a lower value. So this obviously doesn't make sense to be a minimum. Now let's say I'm trying to do a maximization problem. So I have some point here, I take the same thing, I look at my slope, and I'm like, oh, I have a positive slope, so f prime of x is greater than 0. So I can take a step in this direction. And this gives me a larger value. So the only time that it makes sense for a thing to be a min or a max is if the f prime is equal to 0. Because if I'm at some point like this, where my f prime is equal to 0, there's no obvious direction that I can step that will either increase or decrease my objective function. So this is why it's a necessary condition. So I've said necessary, and what do I mean by necessary? There's kind of a formal definition of necessary, and what that says is statement A must be true for B to be true. So I said that the first order necessary condition is f prime of x has to equal 0. So all I'm saying is for something to be a critical point, for it to be a min or a max or the other thing, f prime must equal 0. Just because something f prime is equal to 0 doesn't necessarily mean I have a min or a max, because there's that other thing that we have to worry about. That means that for every min or max that I have, I know that the derivative will equal 0 at that point. So there's this other thing called sufficient. And a sufficient condition says if a statement A is true, then B is also true. We're going to look at what that looks like later on. But essentially what that would say is if I know some property, that means the other property is true, and you can flip the two, which is what you can't do with a necessary condition. Sufficient is a stronger requirement. And essentially what it says is if statement A is true, then B is also true. The first order necessary condition tells us the necessary condition for a min or a max to exist, namely that you have some derivative of f is 0 at that point. But it is not sufficient. It does not guarantee that that point is a min or a max. So now let's look at the second order necessary condition or the second order sufficient condition. So the second order necessary condition says if my second derivative is greater than or equal to 0 at a point, and essentially what that's saying is that I have some point, my derivative is already equal to 0 because I have the first order necessary condition. And if my second derivative is positive, so greater than or equal to 0, that means my function can only stay the same or it can only increase in the local directions. So this is saying that we might have a minimum at x because we have this less greater than or equal to. The second order sufficient condition, it's strictly greater than, so that means that at my point, f prime is equal to 0. So essentially things are controlled by f double prime. And if my second derivative is positive, it can only go up. It can't go down. So I know that that's a minimum, because everything near it has to be going up, and it's at f prime is equal to 0, so it's a stationary point. So we also have the same thing for maximum. Then we have the third thing, which is if f double prime is equal to 0, we have this problem because we don't really know if the function is increasing or decreasing, and that'll essentially depend on the third derivative, which could be 0, which could be dependent on the fourth derivative, and this kind of goes on and on, so we just define this as a thing called a saddle point. So we don't really know exactly what's going to happen at a saddle point. Just to make sure you understand, this is an example of what a saddle point would look like. So this is x cubed. So there's a saddle point at x is equal to 0, because f prime of x is equal to 3x squared, and f double prime of x is equal to 6x. So f double prime at 0 is equal to 0. So we have a saddle point, and essentially you can see here that this point, while the derivative does equal 0, is neither a min or a max, because the function increases either way on either side. So let's look at some examples. So let's say we have this quadratic function like this. So we take our first derivative, so we get 2x plus 3. We take our second derivative, which is equal to 2. So what do we know about this function, and what do we know about the critical point? Well, we can figure out what the critical point is. The critical point is x is equal to negative 3 over 2, because we set this equal to 0 and solve for x. And we know that that point is a minimum, because since this is equal to 0, and this is strictly greater than 0, it is a minimum. And this makes a lot of sense, because if I was to plot this parabola, you'd look at something like this. And this is the point we're talking about. It is a minimum. Now let's look at it from the maximal perspective. So let's say we have the exact same quadratic function, but now our function is negative. Now that we can see that our second derivative is negative, we know this is a maximum. And our graph will actually look something like this, and we're talking about that point. So in summary, the first and second order necessary and sufficient conditions allow us to classify extrema. And this is what I mean when the derivative is equal to 0. So people call these things like local optimums or extrema or critical points. All these different terms are used interchangeably. So while this is really obvious with scalars, and it makes a lot of sense intuitively, the next thing we're going to do is we're going to take it and extend it to the case of Rn. So now let's talk about what it looks like if we have vectors rather than just scalars.